In this lecture, I'll talk about volatiles and their importance to volcanology. Volatiles are gases in magmas that are called variably volatile components, magmatic volatiles, or volatile species. A volatile species can be dissolved in melt, where it's accommodated in melt structure, or they can be present as exsolved species, or bubbles. First, let's look at the eruption temperatures for different composition magmas. In this diagram, we see for a basaltic system, this is pressure and temperature on the axes, we see a solidus and a liquidus. And what these represent are the range of pressures and temperatures above which exists only molten basalt. So this is melt at higher temperatures. Below the solidus, we have only solid basalt. And in between the liquidus and solidus exists a mixture of molten basalt and crystals. This table on the right gives us the range of temperatures over which we move from completely molten magma to a crystallized lava. And it ranges from 1,000 to 1,250 degrees Celsius in basalt to much lower temperatures, 700 to 900 degrees Celsius in rhyolite. Volatiles are defined as those chemical species that at near atmospheric pressure and high temperatures that are appropriate for magmas exist in a gas or a vapor phase. And some common chemical species include water, steam, carbon dioxide, hydrogen, hydrogen chloride, hydrogen fluoride, fluorine, chlorine, sulfur dioxide, H2S, carbon monoxide, methane, oxygen, etc. And there are some noble gases like helium and argon. But overall, water and carbon dioxide dominate. And most volatile species consist of only 6 low atomic weight elements, so hydrogen, carbon, oxygen, sulfur, chlorine, and fluorine. And there are small but measurable amounts of these elements that can be dissolved in both coexisting melt and crystalline phases. If we look at an example from New Zealand of White Island, we can see the breakdown of the percentages of the different volatile species. And as I mentioned, water and carbon dioxide dominate, but there is a significant amount of sulfur dioxide and hydrochloric acid. The table underneath shows in metric tons per day for an example eruption. We're looking at a very large volume of hydrogen and carbon dioxide, and to a lesser extent the sulfur dioxide and hydrochloric acid. Compare that to volcanic gases from rift volcanoes. And if you look at the numbers side by side, you'll see that rift volcanoes have less water, less carbon dioxide, and increased percentages of sulfur dioxide and less hydrochloric acid. And this is going to result from differences in chemistries in those systems. Looking at a phase diagram of water, you'll see that at high temperatures we have water vapor. At higher pressures, that water is in liquid form. And there's something called a critical point that is a particular temperature and pressure where there's no physical distinction between liquid and gas. And exsolved volatiles that are above the critical point are called supercritical fluids. That's in this field up here. The characteristics of supercritical fluids include their density is more like a liquid, their solubility is like those of liquids, they have diffusivities like those of gas, and viscosities like those of gas. But all of those characteristics are still pressure and temperature dependent. As I said, the density of supercritical fluid is very low, and that means the specific volume is very large. And we're looking at volumes of 10 to 10,000 cubic centimeters per gram. And why is this important? This diagram shows pressure versus specific volume for water. We see the density of water is 0.1 gram per cubic centimeter. The density of the magma is closer to 2.2 grams per cubic centimeter. And in erupting low-pressure volcanic systems, the term gas can be used instead of fluid because at depths of less than a few kilometers and magmatic temperatures over 700 degrees Celsius, the density of water is very low, while the silicate melt is much higher. And what that indicates is that the gas is distinct and is a separate phase. So why do we study these volatile species? They play a fundamental role in forcing magma to ascend and erupt. For example, a typical percentage by mass might be 0.1%. That's equivalent to 90% bubbles in the magma. I've shown you this diagram before, and what it plots is pressure versus volume for exolved volatile species. So what we see is that as pressure on a magma decreases, meaning it's moving up higher in the Earth's crust, the volume of the exolved species of those bubbles is increasing, and that when we get to a certain point in this neighborhood, the volume is increasing very rapidly. And what that means is that if we have a rapid decrease in pressure, for example, in the Mount St. Helens eruption, where there was a landslide that removed a lot of overlying rock, that would lead to a sudden increase in the size of the bubbles in these exhaled gases and an explosive eruption. Let's look at the behavior of volatiles in magmas. The solubility is a measure of the concentration of a volatile species that can be dissolved in a melt, so accommodated in the melt structure. And it's a function of pressure, P, temperature, T, and the composition of the melt, X. Most important for solubility are the pressure and the composition. What that means is that for a particular pressure, temperature, and composition, there's a maximum amount of water that can be dissolved in a melt, for example. The volume of a volatile-rich melt is much smaller than a volatile absent melt plus a free volatile phase, so bubbles. What happens at increasing pressure? This pushes the reaction to the side with a smaller volume, and that means that solubility increases with pressure. And an easy way to remember that is the analogy that I've given you of a soda bottle. So before you open the cap, the gases, the carbon dioxide is dissolved within the liquid. But when you reduce the pressure by opening the bottle top, the pressure is reduced and the bubbles exsolve, the volatiles exsolve. Looking at some solubility diagrams for water and carbon dioxide, you can see that the solubility of both the water and the carbon dioxide is higher in the rhyolite than the basalt. So in water undersaturated melts, the volatiles are dissolved within the melt at high pressures, and in a water saturated melt plus water, we see that at higher pressures, small bubbles within the melt, and lower pressures, larger bubbles within the melt. This would be for a water oversaturated magmatic system. Let's look at measuring magmatic or pre-eruptive volatile contents. What's the challenge in accurately measuring or estimating the amount of volatiles in magmas? When gas samples are taken at the surface, they can become contaminated with the atmosphere. And if a magma is saturated and bubbles formed, it lost some of the volatile supply prior to the eruption. This is a phase equilibria diagram for a Mount St. Helens day site. And it plots pressure and temperature and different crystals, so OPX being an orthopyroxene, plagioclase, iron titanium oxides, like ilmenite, and amphibole. As pressure increases, so does the solubility of water. So the temperature at which minerals crystallize decreases. And that's why we have these slopes. At higher pressures, the minerals crystallize out of the melt at lower temperatures. Amphibole is an exception because it's a hydrous mineral, meaning it has structural water. And at higher pressures, amphibole crystallizes out of a melt at higher temperatures. You can also look at glasses and melt inclusions. We can measure the abundances in submarine glasses because little or no degassing happened. Because the magma cools on contact with the seawater. And the melt inclusions, which are blobs of melt or glass, are surrounded by crystalline material. So the interpretation is that these blobs of melt don't lose volatiles because they're armored by a solid crystal. Now let's look at volatile loss from the magmatic conduit. So what's the evidence that we have volatile loss in the magmatic conduit? Well, evidence suggests that magmatic volatiles can be lost from a magmatic conduit while the magma is ascending. The long period seismicity, this harmonic tremors, represent volatile loss to the wall rock. And we see eruption of vesicle pore magmas and the breakdown of hydrous phases during ascent. So how does this happen? Well, there's relative motion between bubbles and magma. The magma viscosity and ascent rates are low enough to allow bubbles to coalesce and rise within the conduit. And this coalescence and migration can allow volatiles to escape into the surrounding wall rock. And that yields effusive eruptions, so lava flows and lava dome building. If bubbles and magma move upward together and the ascent rates are similar, then for bubbles to escape, they need a permeable network that allows the volatiles in bubbles to separate from the magma. And why is this volatile loss important? The ability of volatiles to migrate out of magmatic conduit allows the magmatic system to degas, and so the ability of volatiles to migrate out of the magmatic system is one determining factor in explosive versus effusive eruptions. Why are explosive eruptions more common in silicic magmas? The higher viscosity of silicic magmas means that the bubbles aren't able to migrate out of the magma as well as in less silicic magmas. So rhyolite being silicic versus basalt being less silicic. And the correlation between rhyolitic magma and explosive eruption and the effusive eruptions that you see at basaltic volcanoes like Hawaii. Let's look at bubble growth. Why do bubbles grow? Bubbles nucleate and grow when magma reaches supersaturation. And that's equivalent to when the vapor pressure equals or more typically exceeds the confining pressure. This allows a critical fluid to separate, and that's equivalent to the formation of bubbles. Once the bubbles successfully nucleate, they grow, and the rate of growth is a function of a number of variables, including the concentration of the volatiles, the diffusivity, the density and viscosity of the magma, and the surface tension of the bubble. The size of the bubble, in part, is a result of competition between nucleation and growth. We look at an example of bubble growth in an obsidian. This video shows the vesiculation of a thin obsidian wafer, so about 100 microns, from the 2008 eruption of the Caitan volcano in Chile. The obsidian was heated to almost 900 degrees to study the growth of individual bubbles and to determine the rates of growth. And this is important for understanding the timescales of bubble growth in rhyolite and decoding the vesiculation history of post-fragmentation pumice clasts and bombs. We can watch it from the beginning again. I have an almost bubble-free obsidian. They're growing and new bubbles are nucleating. They begin to coalesce, forming a permeable network within the bubbles. So in idealized bubble growth, that's defined as bubble growth at a constant pressure in a stable, non-moving melt. There are two stages. You have growth by diffusion, which is viscosity limited, meaning that in a more viscous magma, the volatiles are less able to move through the magma. And growth by expansion, which is diffusion limited. Early in the bubble growth history, diffusion is relatively efficient, and the bubbles grow by the addition of volatiles by diffusion. Bubbles can commonly maintain equilibrium between volatiles in bubble and volatiles in a melt. Growth is viscosity limited. That is, although volatiles are diffusing into bubbles, the bubbles still have to expend energy to grow against the surrounding melt. So higher viscosity makes the bubble growth more difficult. In this diagram, we see the radius of a bubble versus time. And stage 1 of bubble growth is referred to an exponential growth stage when the bubble is very small. That corresponds to stage A on this diagram. In stage 2, it's referred to as the parabolic growth stage, and this is when bubble growth slows. This corresponds to stage B, and this is when diffusion of volatiles into the bubble can't keep pace with the growth of the bubble. The bubble growth history falls below the parabolic line in stage C, because neighboring bubbles limit bubble growth by competing for volatiles. The rate of decompression is also very important to bubble growth. At depth in the magmatic conduit, the bubble grows initially by diffusion. As the magma accelerates upward in the conduit, bubbles grow by expansion, and that is, the critical fluid gas phase is expanding against the melt, and the expansion is limited by viscous resistance at the melt and by neighboring bubbles. Thus, an excess pressure develops within the bubbles. The excess pressure can lead to fragmentation. In general, fragmentation is favored by rapid rates of decompression and high viscosity because it's difficult for bubbles to maintain equilibrium, and it's therefore more common for bubbles to become overpressured. And this is why andesitic and rhyolitic, those silicic magmas, are commonly explosive. In general, silicic magmas form smaller bubbles, so 1,000th to 1/10 of a centimeter, compared to basaltic bubbles where they're 1/10 of a centimeter to 5 centimeters. Diffusivity is slower in silicic magmas, and the viscosity is higher, so it's more resistant to the bubble growth. Again, this all pertains to why the more silicic magmas are explosive. If we look at the growth of crystals, phenocrysts form mostly long before an eruption, and they can record mixing effects and magma movements of other sorts. Rapid growth features include skeletal or bow tie crystals, elongate spinifex crystals, and spherulites. I have examples on the right of spinifex olivine at the top, a skeletal olivine crystal in the middle, and spherulites, so these rounded blebs of feldspar at the bottom. The textures in the ground mass of many lavas record events that occur near the surface before an eruption. An examination of these requires high magnification because they're quite small features, and you need to use backscattered X-ray images using a scanning electron microscope or an electron microprobe. As a magma ascends up the magmatic conduit, we first see the bubble nucleation, as in that little video. Then the development of new nuclei or new bubbles and the growth of bubbles. That's followed by this saturation of bubbles in a froth stage, and then fragmentation when the eruption begins. If we look at an example system here of an explosive eruption, and this is magnified greatly, but near the bottom of the eruptive conduit, we see small, sparse bubbles, plus some crystals in a melt. As we move up, we see larger, more abundant bubbles plus crystals in a melt. Further up, near the fragmentation surface, we see an unstable foam of overpressurized bubbles plus crystals. And finally, pyroclasts that consist of euhedral phenocrysts, irregular exploded phenoclasts, and exploded vitroclasts or glass. And these are dispersed pyroclasts in a greatly expanded continuous gas phase.